Hey, hi everyone. Good morning. Okay, let's wait for some time. I think others will join in soon. Okay, we'll start in just 2, 3 minutes. Meanwhile, if you want to discuss anything, we can do that. Any questions as such? Anyone with any questions? Any questions from any of the previous sessions? Okay, I'll presume then there are no questions. Let's start implementing decision trees. So what we'll do is we'll load a simple data set for classification. We'll begin with a classification data set and let's see how we can build a decision tree from that. Okay. So let's pick a small data set. Okay, let's look at some data sets, maybe select one of them. Okay. So this one has 2 classes. This one has 3. This one has 10. And this one has 3. Which one do you want me to pick? Tell me. There are 4 classification data sets. Out of these 4, what shall we go with? Anyone? Yes, people. Okay, since no one is speaking, then I'll probably go with the first one. Okay, let's go with this. So this particular data set is about flowers. Okay. Now, in the you can say the nomenclature, there are 3 types, essentially versicolor, virginica, and setosa. There are 3 classes essentially. Okay, so these are 3 class labels. Okay, you can say these are 3 class labels. Maybe one of them is 0, another one is 1, and the final one is 2. So you would see labels as 0, 1, and 2. Okay, and the features are, I think it's sepal length, sepal width, sepal length and width, and similarly you have petal length and width. So based on the 4 features, these are the 4 features. Okay. Based on these four features, you have to identify if a particular flower belongs to one of these three categories. Okay. So I'll just show you the description as well so that we can confirm, okay, this is the case. So it says that it's an iris plants data set. There are 150 samples, 50 samples in each of the three classes. So you have these four features: sepal length, sepal width, petal length, and petal width. Everything is given in centimeters. Okay, and there are three classes: setosa, versicolor, and virginica. Okay. I want you to focus on some descriptive statistics. You can see that their ranges are different. Okay. And they also mention class correlation. So typically, if the class correlation is high, those features would turn out to be important. Okay. So it means that, okay, petal length and petal width share a very good correlation. Okay. So they will be important features in general. Okay. All right. So I'm going to split this data. So first, let me load this data. So this is where your features are. So this, if you look at this, this would be 150 times 4. Okay. And let's save your outputs. And this would be 150 outputs, one for each sample. Okay. Now our data is ready. Let's split it into train and test. Maybe let's take, say, 20% data into testing. Pass your X and Y, the size of the test set, 20%, and a random state to ensure that you get the same result. And also, you would like to stratify and say the output labels, the output label distribution should be maintained in the splits. So we will get the train and test features and the train and the test outputs. Okay. Now, please note that there is no need for feature scaling for decision trees. For decision tree or any of the models which is based on decision trees. Okay. The reason is like when you are computing the threshold for a feature, right? Even if you scale it, only the threshold would change. The feature would still remain to be that much informative that it was previously. Okay. So the values of entropy, or let's say you're computing Gini, that's not going to change, no matter whatever thresholding or say whatever standardization or normalization that you do. Only the thresholds would change. The rest, everything, the decision tree structure is not going to be impacted. Okay, so there is no need of any form of scaling of your feature data. All right. So we'll not be doing standardization or normalization. Even if you do, you can see that, okay, results will not change. All right, so let's apply our decision tree model. So decision tree is present in sklearn.tree. And let's import this decision tree classifier. So you know that we can use it for regression as well. Second. So let's call it maybe say decision tree classifier, DTC. I'm going with the default model. I'm specifying a random state to ensure that you and I get the same results. Okay. Let's fit the model onto our input and output. Input is in the train set, output is in the Y train. Model is fit. Let's try to predict from this model. 1 second. So you can say DTC.predict, pass the test set. So these are your test predictions. And now you can compute any metric that you want. So before I do that, I'll show you decision trees can help you predict probability scores as well. Okay. So you can pass the test set. For each sample, you will see that there are three probabilities because there are three classes. Okay. So for each sample, you can see that there are three probability scores. Currently, they are 0, 1, and 0 because you are, fully growing the decision tree. Okay. So maybe in the leaf nodes that you get, they are all pure. So if they are all pure, you will get the probability score as 1 for one of the classes. And for other classes, it would be a 0. Okay. So these are the predictions in terms of probabilities. So this is class 0, class 1, and class 2. Okay. Let's say you want to compute some metric. I'm interested in computing, say, accuracy score. So let's compute the accuracy score for this model. So pass the actual values, the predicted values, and this is okay, my bad. This is your accuracy score. So the decision trees are doing very, very well. Okay, a fully grown decision tree does very, very well on this test set. Okay. Now let's try to tune this decision tree. So if you remember, to tune this decision tree, we can actually do pre-pruning. Because fully grown decision trees are likely to overfit. Okay, so it is okay to, you can say, reduce the size of the decision tree. So we can have, so let me first show you how the decision tree looks like. Okay, you can actually see the decision tree. There is a function which is called as plot tree. Okay, and this function can help you visualize how the decision tree looks like. Okay, so you can pass the decision tree classifier to it. And then you can say, okay, plt.show, and this will, plot the decision tree for you. What I'm going to do is I'm going to maybe increase the size of the figure. Okay, because the number of levels in this decision tree can be very large. So it will not be visible clearly. Maybe say 15,15. Let's see. Okay. Maybe let me increase this a little further. Let's 30. Just a second. I think I have to do it before this. It's not changing. Yeah. Can you see it now? Is the plot visible to everyone?
Yes.
Okay. So what you can see is like the very first feature that is used is X3. X3 means it's a fourth feature. 3 here denotes the index. This is the threshold that was used. This is the Gini impurity of the parent, this particular root node. So this much is the Gini here. Okay. So there are a total of 120 samples in this node, and the distribution is 40, 40, 40. So each of the classes has 40 samples each. Okay. Then you use this feature X4 to split it, the fourth feature to split it, and the threshold is 0.75. You go to the left, this is what you get. So here you can see that class label 0, it has all the 40 samples, so this becomes a pure node. Okay. On the right hand side, you have the distribution as 40, 40. So class 1 and class 2 have equal samples. Then you are using the third feature at X2 with the threshold as 4.75, and then you are splitting it further. So this is the complete tree that you get. Okay. And with this complete tree, you have an accuracy of 96.6% on the test set. So this is the test set accuracy. My objective is to improve upon this. Okay. So what I'll do is I'll try to tune it. So to tune it, you need to know, you need to call, you can do a grid search. Okay, that is something that we can do, but that will be running on 10 folds or 5 folds, right? Some number of times. I'm going to do it for one time only, okay? Because I want to show you that you can improve upon this performance, okay? You can improve upon this performance. I'll be doing it on this test set only, okay? So what I'll do is I'll create my list of parameters You can call it as hyperparameters. So these are my hyperparameters. Okay, so the first one that I will say is, okay, max depth. So you can limit the depth of the decision tree. You see currently what is the depth? Let's see, 1, 2, 3, 4, 5, 6 is the depth right now. So I can actually check for up to say, maybe say 3 to 6. Okay, I'm checking for this as the range of my max depth. Okay, so let's say I'm going to go with this. So in range, last value is not included. So this is my, let me call it, say, my M depth. Okay, the parameter named is max depth. Okay, this is one thing that I will be checking. You can check, say, the minimum number of samples that have to be in a node for you to split. That is called as min samples leaf. Sorry, min sample split. It has to be the minimum number of samples that has to be there for you to decide whether you are going to split it or not. So this you can provide. So let's say I'm going to put this condition as a value between, say, 2 to at least 2 samples have to be there to split, right? So if it is 1, there is no need of splitting it. Maybe say 2 to 5. Okay. So let me call it M underscore samples underscore split. Okay, this is all right. We can take maximum number of leaf nodes. So currently, how many leaf nodes do we have? 1, 2, 3, 4, 5, 6, 7, 8. And is there anyone above? 9. Okay. 9 leaf nodes we have. So you can put a range on leaf nodes as well. I'm not going to do that. The depth will actually take care of it. Okay. You can try with different criterions. So let's call them as, say, CRIT. Okay. So you can say my criterions are Gini, maybe say entropy. So by default, the criterion is Gini, as you can see above. See, we are computing Gini for this, right? So if you are using Gini, that is called as classification tree 4.5. If you are using entropy, that is the iterative dichotomizer version 3 algorithm. So you have Gini, entropy, and then you have log loss. Okay. So these are the things that you can try. Okay, this is called as criterion. Okay, you can think of what is the minimum entropy or the minimum Gini that is to be there with the help of which you split the data further. So that you can put. So I'll show you maybe all of them. Okay, we have discussed about all of them in the theory. But implementing them is just going to take more time. So you can try it in your free time. Okay. See, we have seen criterion. This is what we can do. Okay, this is nice, splitter. So splitter means that, so let me call it split type. Okay, so splitter supports best and random. The idea is when we are building a decision tree, we typically take the best feature, right, at the top. So by default, this value is the best. Okay. However, if you want to avoid overfitting, you can actually pick a random feature to create the tree, and that you can call it as a randomized tree. So that is what split type is. Okay. So it decides what feature you are going to take to split your partitions further. All right. So we can try with both best and random. Then we have seen max depth. This I have already talked about. This is when min samples leaf is when you are creating a new child, right? When you are creating a new partition, at least these many samples have to be there. So default value is 1, which means that it is as good as creating a leaf node with entropy equal to 0. So you can increase this value. And please note that this value has to be smaller than this value. Okay, if it is larger, then it will throw an error. You can think why. See, upon creating a new partition, if you put this value as three value, I mean, three number of samples, three samples at least have to be present in a new node. If this value is 2, it doesn't make sense, right? It has to be more than 3, only then you should split it and then you will get the criteria, okay? The new child should have 3. So keep this value smaller than this. It's not very useful though, you just try with this min sample split, okay? This is the, currently it is 0, which means that you are ending up in pure partitions. So this is the percentage of samples for the lowest class, okay, for the least class. So if I look at this, okay, maybe I'll show you a small example. If I ask you, look at this node, which I'm currently highlighting. If I ask you, maybe not this node, maybe something else, where I have all the 3. No, not that doesn't make sense. Okay, maybe look at this. Can you tell me which class has the most number of samples in this leaf node?
Third class.
Class 2, right? Class 0, class 1, and class 2. It has 2 samples. Which has the minimum number of samples?
Class 0.
Class 0. What is the percentage of samples in class 0?
0.
0%, right? This one has 33%, this one has 66%. Does that make sense?
Yes.
Okay. So if I ensure that the minimum class is class 0, right? The class having the minimum fraction. Okay. This is class 0. 0 is the percent. So if I make this number as say 0.1, which means that every class will have at least 10% of the sample. Every class will have at least 10% of the samples. That's what this means. Okay. So currently it is 0, which means that we are moving towards pure nodes. Okay. Minimum weight 0 signifies that we are okay with one of the classes being a 0. All right. You can increase this number and that will reduce the size of your tree. Then you have max features. This is important. The idea is, let me just talk about this. See, let's say we are at this root node. Can you help me recall how do we decide the best feature? We are using Gini impurity. So what do we compute here? What do we compute for the root node? How do we decide which feature is to be used? Anyone?
Using each feature, we calculate the Gini, and for whichever the impurity is minimum, we take that feature for the split.
Yes. So what you do is you compute the information gain from this Gini criterion. And whichever feature minimizes this Gini impurity the most, or you can say maximizes the information gain the most, that is the one that we pick, right? So currently we are actually looking at all the features. Does that make sense?
Yes.
Okay. Now you can have this value which is called as max features. Okay, let me call this as M features right now. What you can do is that instead of looking at all the features, can I say that I will look at maybe say 70% of the features. So 70% of 4 features would be how much? This would be around 2.8, right? So 0.7 of 4.
Yes.
So 2.8, if you take the ceiling of it, that will be 3. So you're taking 3 features, not all of them, and then selecting the best out of those. So what this means is that instead of looking at all the features, why don't you select 3 features at every node? And then you see which is the best out of that. And go with one of those, go with that best feature out of the 3 features that you selected. Okay. So I'm going to put different values here, maybe say 0.7 and then none, maybe say 0.5 also. So 0.5 will be 2 features. Okay. None means you are using all the features. You can put a 1 here also. Both will mean the same thing. Okay. Both will mean the same thing. 1 means that using all the features. So this means, yes.
Can any 3? Randomly any 3?
Yeah, it will pick randomly any 3 features out of the 4 for every node.
So first using M features, it will pick randomly, and then using split type best and random.
Yes, it will decide how to go about it. So if the split type is best, it will pick the best out of. So let's say if you're using this value, 0.5. So how many features will be selected out of 4?
2.
2. So out of those 2 features, whichever is the best, you go with that. If you are doing it at random, then one of the two features would be selected.
Okay.
Does that make sense? Okay. So this way you can actually induce like more regularization in your decision trees. That way it will tend not to overfit. Okay, this is the random state, so you get the same results. Okay, I mean, if you fix it, if it's the same as mine, you will get the same results. This is the maximum number of leaf nodes. This is how much impurity should be there for you to split it. Okay, currently it is 0, which means that you are moving towards a pure node. If you set it to 0.1, so then if a node has less than 0.1 Guinea, you are not going to split it. This is class weight. So typically a higher class weight is given to minority class. All our classes are how much? Can you see in the original decision tree? What is the distribution of all the classes? 40, 40, 40, right? They are all equal. Okay, so there is no need to give class weight. So you would give higher class weight to that class which has less number of samples. And then you have CCP alpha. I will do it separately. This is for post pruning. It's cost complexity pruning alpha. Okay. So I'll do it separately for post pruning. Okay. So these are the hyperparameters that I'm going to use. So essentially, I'm going to run maybe say 5 for loops. Okay. So let's say for I in say M depth, for J in this M sample split, for say K in this criterion, for say L in this M features, and for say M in the split type. Okay, so I'm going to call my decision tree. This is a decision tree classifier. So assign the max depth to I. Okay. Then min sample split to J. Criterion to this K. And then you have max features as M. And you have splitter as what's the name? It's IJKL. This is L. This is M. Does this make sense? What we did. So we are basically running a for loop with all these different hyperparameters. We are fitting the decision tree, and then we will compute some accuracy. So this is, let's say, the accuracy that we are computing. Okay. All right. Let me store all the accuracies. Let's call it as ACC list. Okay. So we are going to store these accuracies in this list of my bad. Okay, we have appended the accuracies, and let me start a counter here. I want to print the combination number. Okay. So let me print the following things. Let me print the combination number, which combination it is running. So combination number is currently this counter. Okay. Then I'll print the combination. Okay. Let's say this is the combination I'm starting with. So the first thing that we will see is, 1 second. So first thing that we will see is the depth. Okay. So I'll just print all the things side by side. Okay. So you can get the idea. So the first thing is here, this I, which is depth. Okay. The next thing is your J. Okay. And next thing is your K. Then L. And the final thing is that, and this is where I close it. Okay, and then give a space. Okay, so I'm printing the combination number and then I'm printing IJKLM. Okay, these are the combinations. And I'll print the accuracy values. So this is my accuracy value, ACC of counter. Counter is 0 initially, and then I increment the counter. So for each iteration, I am printing the accuracy value along with the combination number. Okay, let's see this. There's a problem. Okay, I made a mistake somewhere here. Min sample split. Okay, feature spelling is wrong. Okay, can you see that now for different values I get different results? There is one thing, what it says is that, okay, log loss is provided incorrectly. I have to check it, it's log underscore loss or log hyphen loss. Okay, one second, it's log underscore loss only. What's the point? Did I mention it incorrectly in here? No, right? It's log loss only. What is the error thrown? It says key error log loss. Just a sec. I'll just copy this. Okay, just a second, what does it say? Okay, I got it. So this one, the log loss implementation that it is, right? It is binary log loss. Okay, it is not the multi-class log loss. So it will only work with binary data sets. Please note this. Okay, the one that is implemented in decision tree, it is the binary log loss. Okay, so this log loss that you see, it's the binary log loss. Okay, not the multi-class log loss that we discussed. So you can just remove this for now. I'll just make a comment here. Okay. For binary classification, you have a log loss also. All right. Okay, so these are the combinations that it prints. Okay. So I don't see it's going higher than, no, there in some cases it is touching 1 also. Okay, in some cases they're touching 1 also. So we have printed all the combinations. Let's look at, so these are their respective accuracies. Okay, I'm going to find the max one. All right, the maximum is 1. Let's look at the index of this. So this is your combination number, the very first combination number where you achieve a 1. Okay. So 37, look for the 37th combination. This is the 37th combination. So this was the first place where you got a 1. You can see that at other places also you have a 1, but maximum returns the very first occurrence. Okay, the index returns the very first occurrence. Okay, so this is the combination that you can use to actually deploy on. So first train your model with all the data using this combination, and that way you can get what we say is the best model. Let me put a separator here as nothing. Okay, so that way you'll see. All right. Okay. All right. So this thing is done. Any questions about decision trees so far? Yes. Any questions about decision trees so far? All clear? Tell me, please. Are you guys hearing a construction sound at the back, like from my mic? Can you hear someone using a hammer?
No,
Okay, that's good then. Okay, I have good earphones then. All right. Okay. All right. This is the best decision tree that we obtained for this particular combination, the 37th combination. I'll just highlight this. The best combination number was 37. All right. This was done using pre-pruning. Let's implement post-pruning. So you don't have to do much. Just one parameter is sufficient. Okay. So in post-pruning, you will just use CCP alpha, cost complexity pruning alpha. Okay. So CCP alphas, I'm just renaming it like this. So you can try for different combinations. Let's say I'm starting from 0. 0 means fully grown tree. Okay. I'm going up to say 0.1, maybe say taking 100 values in between, say 101 values in between. And this time I'll just use this one for loop. Okay, let's say for I in CCP alphas. Just put here CCP alpha as your I. Okay, and rest everything will be the same. I'll just mention here your just a second. Let's say this is CCP alpha. This is your I here. And then let's close it. Give a space here. Okay, and we can say separator is this. Yeah, this is fine. Okay, to print for all different CCP alphas, what is the result? Okay. So these are the results that we get with different CCP alphas. Okay. You can see that these are different CCP alpha corresponding to the CCP alphas. These are the results. Let's find out which one is doing better. Find out the max value of your accuracies. So in this case, it's not doing better than this. Okay. So maybe what I'll do is the values are of this order, right? 0.001. So what I'll do is I'll reduce this value a little further. Okay. So I'll go with maybe say 0. From 0 to 0.001 and 0.0001. Let's start with this. Okay. 0.01 up to this 0.0001. And I'll go up to 101 values in between. Okay. Let's see if it can beat this. If it can take it to 1. Okay. It doesn't look like it. Okay. It's still there. Let me reduce it even further. It means that we want to reduce the CCP alpha to a very small quantity. Okay. I should have taken it the other way around. My bad. So it is still close to, I mean, all the values are 96.67. So basically, it's not eliminating any tree. Okay. Let me just try between 1. Do we see a 1 anywhere? No, it's still the same. Let's make it say. So with CCP alpha, I mean, it's not helping much. Okay, it's the same tree that we get initially. Same thing that we are getting. Okay. Let's try with this last value. Okay. This is the last time I'm trying this, okay? So I'm maybe taking 10,000 values and just running it. Yeah. So if I get a better result, close to 1, that is good. Otherwise, we have the same decision tree. So CCP alpha is not helping here. Because the idea is you are making use of the train accuracy. Yeah. To decide where to stop. Okay, this is kind of almost done. Yep, this is done. Let's see if we touch a 1 anywhere. No, this is the same. Okay. So it's not helping. Okay. CCP alpha is not helping for this particular task. All right. This is your post pruning. For most data sets, I would say CCP alpha will also give you almost the same result. Okay. Any questions about post pruning or anything? Yes, people. Any questions about post pruning? Should I move further? Should I move ahead?
Yes.
Okay. So this was all your decision trees for classification. The only thing that you need to change is, so I'm going to show you for a regression tree now. Okay. I'll import a regression data set and I will just run this. Okay. Right. So let's import a regression data set. Maybe say this one. I'll go with low diabetes. Okay. So I'm going to import this regression data set. Most of the hyperparameters will be the same. Okay. So after loading the data, I'm splitting it into 2 parts, train and test. It's a regression data set. Okay. I'll just give it a title. Okay, just a second. All right. So data is ready. Splits have been made. You can do depth min sample split. Criterions will change. Features split type, they are essentially the same. Okay. So let's look at the criterions. Okay. So you will see squared error, absolute error, Friedman MSE, and things like that. So by default, it is square error, which is equivalent to minimizing the variance. Let's try with all of them. All right, let's look at these criterions. Please change the codes, okay? Otherwise, you will get an error. These codes are not recognized in Jupyter Notebook. All right. I think we are ready. We just have to provide the name of the function. So from sklearn.tree, you have to import decision tree regressor this time. So take this decision tree regressor and replace it with this function. Okay. All right, looks all right. Let's see. There's an issue somewhere. Uh, what's the problem? It says that I cannot handle a mix of multi-class and continuous targets. This diabetes data set. Just a second. This is a regression data set, right? Yes. So what's the problem? Okay, let's call it a DTM. Oh, sorry. Just a second. Oh, sorry. I'm looking at accuracy right now. That's the problem. Okay. What is it that you want me to compute? For a regression task, what is it that you want me to compute? Give me some evaluation metric.
Mean squared error.
Okay, let's go with mean squared error then. So metrics import mean squared error. That was a mistake. So let's call it MSC. Let's call it MSCs. Okay. So this would become MSCs. This would become mean squared error. And this would be MSCs. Okay, this one problem.
It should be small.
Yeah, it should be small. So these are the results of your mean squared errors. Okay. So let's try to find out the best combination, which would be the minimum in this case, because lower the better. So this is the minimum value, which is 0, which means that your results are almost perfect. Okay. They are perfect rather. Okay. So let's get the index of this minimum value, which is 229. Look at the 229. This is the first index where you get a 0. Yeah. Which means that decision tree is performing perfectly on this combination. Okay. All right. Let's do post pruning. So this was pre pruning. Okay. Let's mention it like this. So this was pre pruning. Okay. Let's do post pruning. I'll just okay. Let's do post pruning now. Okay, so for postponing, you just need to provide CCP alpha. Rest everything will stay the same. So let's change. Just provide CCP alphas. So I'm going to try for from 0, which is a fully grown tree, and going from, I'll say, up to 0.1. Maybe I'll go up to 0.05. Okay, and then I'll limit this tree with, say, 100 different values of CCP alpha. Let's see which is the best result. Okay. So these are different combinations for different values of CCP alpha. Sorry. The last values are printed actually. Okay. Is I here. Okay, looks all right. So different values of CCP alpha, these are the mean squared errors. Okay. So what's the least value that C? Around 0.0314. This is the least value. And at what index it is? Let's get that. At the 9th index. This index, we get the first less value. Okay. Maybe you would like to search in this range. So it is around 0.0045, which means that it's very small. So maybe you can go for like this, okay, and search for 100 values in between, okay. Yeah. I hope we are able to reduce this value a little further. So previously it was 0.031. Let's see what is our current value. No, it's the same. Okay. At what index do we get this? It's at 81. So 81 is this much, around 0.004. That means around 0.004. Okay, just a second. I don't think we are able to reduce it any further. Okay, maybe let's try a little bit more. Yeah, 318. Is it the same now? Yeah, it's the same. Okay, so even for different values, let me go with a little higher because 0.007 is also returning that value. Yeah. Let's try with 0.01. Even 0.01 is also returning the same value. As you can see, we can go a little higher. Okay. So let's try for maybe 0.1. It's the same. Okay, and what index it is? At index 0, which means now we have gotten it too much. Okay. So at 0.01, we get the best results. Okay, but up to what value we get 3.31 for it? We are getting at like this value, which is around 0.02. Okay. Beyond this, the value kind of increases slightly. So I will try in this range 0.022. Okay. Okay, this is the last search that I'm doing. If not, this would be the best results that we obtain. It's the same, okay. So it's not helping much. Even after doing a good amount of research on this test set, CCP alpha gives you, this is the mean squared error, which is around 0.03. Quite low in comparison. Okay, very low in comparison. So any other questions? Yes, people. Any other questions about this? Survey, do you have anything? Is the code clear to everyone, like whatever we have done so far? Yes, people. See, I've been writing and I've been trying to describe, okay, what is it that we are doing, but I'm not sure whether you guys are able to follow it. Is the code clear to everyone what we are doing? We are just passing the hyperparameters one by one, training the model with that particular hyperparameter combination and getting the results. I'm just running for loops, nothing special. Any questions as such?
No.
Okay, let's start with our next topic, which is ensemble learning. This is the next topic. The heading of this. So, ensemble learning is a domain where we train multiple models. Okay, the idea is instead of using one model, we will combine the predictions of multiple models. Okay, so if you think about it, these models can be, say, multiple decision trees. These models can be, say, one logistic regression is there, one decision tree is there, one support vector machine is there, one say Naive Bayes is there. So there are many different algorithms that you can use, that you can combine. Okay, so if you combine the models that are coming from the same algorithm, then it is called as homogeneous ensemble learning. Homogeneous ensemble learning. Or you can simply call it homogeneous ensemble. Ensemble means a collection. Okay, so when you can say underlying ML algorithm is the same for all models. So we are building, say, multiple decision trees or multiple logistic regression models. Can you tell me which model, which technique that you have studied that creates the homogeneous ensemble? Which technique you have studied which creates a homogeneous ensemble? You have seen 2 or 3 strategies like this.
One versus one versus rest.
Yeah, and error correcting output code classifier. So those are homogeneous ensemble algorithms. Okay, you can treat them as ensemble learning. You are combining predictions of multiple models. Okay, the idea is like our objective is to get a improved prediction. Okay, to get you could say performance improvements. All right, and the other setting is heterogeneous ensemble when the models are different. Okay, when the algorithms that you do use, they are different. Okay, let's call it heterogeneous ensemble. So I'll show you for both how to make them. Okay, when the ML algorithms, when models are coming from different algorithms, you can say. Okay, so this is just a second. These formattings are something. Okay, so you once you refer to this notebook, you'll be able to get this. Okay, all right. So let's start with a simple scenario and discuss how you can combine multiple models. Okay, it's not very straightforward. So let's see a scenario where you are going to combine multiple decision trees. Okay, let's see that. Okay, you are going to combine multiple decision trees. So let's say you have d p number of trees. Okay, let's say p is the number of trees. Okay, p is the number of trees, the number of models essentially that you are going to combine. Okay. My question is this. When you are creating multiple models, do you want the models to be the same or do you want the models to be different? do you get any benefit if the decision trees are the same?
No.
No, right? So essentially, when we are looking at the combination of different entities, the entities should be diverse, right? So what is it that we need? We need diversity, right?
Yes.
Okay. So when I say combine the prediction of multiple models, I will say that these models have to be diverse. Okay. All right. Diversity means that their prediction should be different from each other. If they are the same, then I get no benefit. Okay. So it's like saying that I have 10 people, maybe out of 10 people, say 6 people say 1 and 4 people say 0. But the majority is still a 1, right? So whatever the majority says, I will go with that. But if everybody says a 1, okay, I mean, even though it's a good thing, I'm not saying it's a bad thing. But if everybody says a 1 all the time, do you think it's a good thing?
No.
No, right? So there has to be diversity in the models. So models should be, so when I say there is diversity in the models, what can you say about the training set of these models? Will they be the same or different? The data on which these decision trees will be trained, it will be the same or different? If it is the same, don't you think you get the same decision tree?
Different.
Right? So it has to be very, very different. Okay. So typically what we do is we start with, say, a data set, right? I mean, any task that we are given, we will have a data set and we will split it into 2 parts, right? Train and test. Okay. So data set is split into 2 parts. Okay. In general, I'm saying. So if I give the same training set to everybody, then all decision trees will turn out to be the same. So I will not get any performance improvements. Okay. So imagine my data set contains 1,000 samples. Okay. Just for a simple analogy. Okay. So you split it into 2 parts. Let's say 800 go to here in the training set and 200 go here. Let me say this is 1,200. Okay. And this is 1,000 and 200. Okay. My question is this: how can we ensure that decision trees are different? If in the training set I have 1,000 samples, so this is the data that I'm going to use. Okay, this is the data that will be used for training your models, right? Yes or no? The train set is what I use for training the decision trees, right? This is the model that is used to train your decision trees. If I pass this data set as it is to each of the decision trees, will there be any change? No, right? All of them will be the same. So can you tell me what should we do?
Fold.
We should?
A-fold split so that we have different training set every time.
Okay, that is one way to do it. But then you are saying that I am having train and test sets to be different, right?
Yes.
So if the test sets is different each time, see, I want the result on the same test set for everybody. I want the results on the same test set for everybody. How do I do it then? Think about it. Somebody has given you this 1,000 samples, okay? How will you make these decision trees and ensure that they are different?
You can further split this train data.
Yes, you should further split this train data. One idea is, okay, think about this. See, if I make, say, if number of trees are P, and I simply divide this 1,000 by P, let's say P is 10. Assume that P is 10. So how many samples will each tree get?
100.
100. Do you think with 100 samples I will get a good tree?
No.
Each decision tree would be very bad in that case, right? Yes or no? So you have to combine good models, right? You cannot combine bad models. Does that make sense? So if you want your decision trees to learn well, I cannot just directly just split the data into partitions and give 100 samples to each decision tree to train upon. So the idea here is, why don't we, okay, do something called as random sampling? Okay, so let's select maybe say 800, maybe say 700 samples at random. Okay, maybe select 700 samples at random out of 1,000. and give it to D1. And then I select 700 samples at random again, give it to D2. Do you think these decision trees will be different now?
Yes.
Likely to be different, right? If I increase this number, let's say I make it 900, do you think they'll turn out to be different?
Very little.
Very little, right? Okay, think about this. If I give you a decision tree, or maybe say a training set with 1,000 samples and another one with same, I'll just remove 1 or 2 samples. Do you think decision trees will change drastically? If I remove 1 or 2 samples, do you think decision trees will change drastically?
No.
All right. Okay. So it's not going to change very, very drastically, right? In most cases, I should say. In most cases, it can change drastically if you deliberately decide to remove 1 or 2 samples that change the structure drastically. But if you pick the samples randomly, they are not going to change much. Because what do you think the impact on entropy? See, don't you think that the same feature, which is the best feature for 1,000 samples, will be the best feature for 999 samples also, for 998 also, maybe for 900 also? Yes or no? Does that make sense?
Yes.
Okay. So if I increase this number, what happens is diversity reduces, right? If I increase this number, diversity reduces. So if diversity reduces, it is of no point to me. But if I decrease this number, then diversity increases. Yes or no? But what is the problem then? Each decision tree doesn't get to look at a lot of samples, right? Each decision tree would be very bad because it has seen only a few samples. Do you realize that?
Yes.
Okay. So there is this big problem if you do random sampling. So that is why what we do is, what we say is random sampling with replacement. Okay. What this idea says is this. Okay. You can select, okay, 1,000 samples back again from the data set, but this time you can have duplicates. Okay. So imagine you have 1,000 places to fill. Okay. You have 1,000 places to fill. So so in the first place, what you are going to do, so imagine there is a bag where you have 1,000 numbers. Okay. 1,000 bottles. You put your hand in the bag and take out 1 bottle. So can I say that maybe third bottle comes out? Yes or no? Is it possible that the third bottle can come out of 1,000? So I'm just noting down this number. So I saw the third sample. Okay. Now what I will do is I will keep the 3 back again in the bag and will shuffle the bag. And is it possible in the second place, maybe say 5th comes out? After seeing 5, I will put it back in the bag. Will shuffle it. Is it possible that I see a 3 back again?
Yes.
Okay, so they are duplicates. That is what the replacement is. Okay. See, when you are simply doing random sampling, if you take out the 3, you are not going to see 3 again because the bottle will be taken out. The sample will be taken out. Okay. But with replacement means that you can have duplicates. Okay. So do you think that this strategy can ensure that every decision tree gets to see a lot of samples and they are still very different?
Yes.
Okay. And there is one advantage of this. What do you think the advantage is? There is one better advantage of this. So can I say that if a particular decision tree is focusing on, say, is having a lot of duplicates from, say, sample 3 and sample 5, can I say that it is focusing more on sample 3 and sample 5?
Yes.
Okay. It's like saying you are giving more weightages to these samples. So different decision trees will focus on different samples. Yes or no?
Yes.
Their tendency will be more towards focusing on a certain group of samples, right? So they are focusing on different parts of the data. Okay. And obviously, like if they are focusing on different parts of the data, now if you are looking at a smaller data set, do you realize that these decision trees will likely to do well in their respective regions? Yes or no? So assume that if the test set arrives from that region, so if assume that this is the decision tree for D1, you build a decision tree D1 from this. If you have a test sample which is close by to this sample 3, so do you think that that sample will always get predicted correctly by D1? Yes or no? Because it will fall in that same partition, right? Because it is closer to 3.
Yes.
Okay. So you can say that some of the decision trees, like because they are focusing on their respective regions. So a single person, see, I'll give you an analogy here. A single person will find it difficult to learn from all the samples. But now, since you're having multiple people, multiple models, they can focus on their respective regions and they can actually do a better job in that region. Does that make sense? Do you think that a single person can study all the topics, let's say it will be better at all the topics in a given exam? Do you think that a single person, like even if the person is, let's say, like Einstein, do you think Einstein knew everything?
No.
No, right? Okay, so the idea is now you're having multiple individuals and they are expert in their respective regions. And what we are trying to do now is, even if, say, more than half of them, they agree on a particular number. Let's say you're doing binary classification. Can I say that if more than half of them agree on the majority of something, then I will get a better result, maybe using a single person? Yes or no? It may help, right? Most of the time it will. Okay, most of the times it will. So an ensemble learning model makes use of the strategy random sampling with replacement, okay, to build your decision tree models. Okay, and this number, even if it is very high now, okay, even if it is close to 1,000. See, I'm picking 1,000 samples from this set of 1,000. Okay, and despite that, the samples that you will see will be very different. So the training sets will be very different. Okay, so decision trees will turn out to be quite different from each other. By the way, if you are interested, there is a proof. There is a mathematical proof. Okay, let me just give you this proof in simple words. Assume that you have n samples in your data set, in your training set, and you are picking n samples with replacement. Okay, you are picking n samples with replacement. If n is a big number, let's say if n tends to infinity, okay, if n tends to infinity, what is your guess that how many samples we will not see in a training set? How many samples, what percentage of samples do you think you will never touch? There is a mathematical proof for this. Okay, let me ask you this. Assume that you have 10 samples, okay, and you are going to select 10 samples with the replacement. Is there a guarantee that you will touch all the 10 samples?
No.
No, right? Okay. So let's say you don't select, you never touch, say, 2 samples. So what percentage you did not see? 20%, right?
Yes.
Does that make sense? Now increase this number to 20. If you select 20 out of 20, is it more likely to happen that you will see a bigger chunk which is unseen or lesser chunk which is unseen? Now you are selecting 20 out of 20.
Lesser chunk.
Lesser chunk, right? So can I say that you are going to see lesser and lesser number of samples as I increase this number?
Yes.
Okay. Lesser fraction, I should say, right? Lesser percentage. So what will happen if I make sure that, okay, n is a big number? Let's say the number of samples in a data set are, say, 1 million, and you are going to select 1 million samples with the replacement out of it. What percentage do you think you will never touch? Just take an estimate, okay? There is a mathematical proof for it. It's a question based on limits.
Somewhere close to 0%.
No, why it would be 0%? See, I think you took it the other way around. Okay, think about if there is one sample and you are going to select one sample out of it. Did you miss anything?
No.
Let's say there are 2 samples. If you select 2 samples out of it, what is the chance that you will select both of them? Very high, right?
Yes.
Okay. If I select 3 samples and I select 3 out of it, what is the chance that I will see all the 3? Really good chance, right? Really high. If I select 4 samples and you are selecting 4 out of it, what is the chance that you will see all 4? Do you realize that it becomes really each time as I increase it? So the chunk is actually unseen. The fraction of data, if you increase n, right, it actually increases. It doesn't decrease. Yes or no?
Selection increases and unseen part decreases.
No, it's the other way. You will be getting more and more duplicates. That's what I'm saying.
Okay.
You'll be getting more and more duplicates. See, the chunk which is unseen will become bigger and bigger. The fraction of chunk that you will not see will become bigger and bigger. Don't you think it is quite intuitive as well? Okay, let's do a simple experiment. Okay, you have 10 bottles in a bag. You are going to take out 1 bottle at a time, and then you are going to put this back again. Do you think that if you take out 10 bottles from this bag, you will see all the 10 bottles?
No.
No, right? Okay. Let's say that, okay, you didn't see one bottle. So what fraction was unseen? 10%?
Yes.
Does that make sense? Okay. Now I give you 20 bottles and you are going to take out 20 bottles from it. Will you see all the 20 bottles?
No.
Very unlikely. And is it okay to say that you will not see 2 to 3 bottles?
Yes.
So maybe say I'm saying you don't see 3 bottles. What is 3 out of 20? Around 15% now.
Yes.
Okay. Does it make sense?
Yes.
So you actually didn't see bigger portion. So I'm saying if you now keep n to be say 1 million, what do you think? Is this fraction going to increase or decrease? This fraction will always increase, by the way. Okay. In general, this fraction will always increase. What is your best guess? What percentage of data you will never touch? Give me your guess. That's what I'm asking. Give me enough. How much?
99%.
No. It's not that high. It's not that high. Okay. If you say 99%, then you are saying that, yeah, let's say if you have a bag of say 1,000 samples, you are saying that I will just get to see basically 10 samples. Right? That's what you meant, right?
Yes.
No, will you just see 10 samples if you pick 1,000 times? No, right? You'll see a lot more, right? Okay. So if you want to prove this, maybe I'll share it with you. I mean, it's a little difficult to understand if you are not from a mathematical background. I have to teach you limits. I don't want to go that far. Okay. People study limits in their 8th, 9th class. I don't know if you remember this or not. But if you remember limits, you can understand this derivation easily. The number that you will see is actually 1 by e. This is the percentage that you will never see. So this is around, I think 34% or so, or 36% or so. Let me just see. What is this number? So it is around 36.7%. So around 36% of the samples you will never see. Okay. Is this part clear? So 1 by e of the chunk, or you can say 1 by e percent of the data set will never be seen. So you can say that from 1,000 samples, 367 samples will never be touched. Okay. But please note that n is a big number, not 1,000. Okay. So from 1 million, you can say that, let's say from 10 lakhs, you are not going to see 3.67 lakhs. Okay. From 10 lakhs, you are not going to see almost 3.67 lakhs. It's a huge number, right? Can I say that 1 out of 3 samples you will never see? Yes or no?
Yes.
Okay, so this number is a very big. So can I say these decision trees will be very, very different in that case? If you had more samples in your training set. If this number was really big, currently it is 1,000, right? If this number was really big, the data sets will turn out to be very different. Okay. All right. So another advantage of doing this random sampling with replacement, this is also called as, by the way, bootstrapping. You're bootstrapping your data, okay, from your data set. Okay. Bootstrapping means simply selecting with replacement. Okay. There is one more name for it. This is also called as instance bagging. This is also called as instance bagging. The name itself tells you that you are trying to bag the samples from you are trying to collect the samples, collect the instances from a bag. Okay. Please note that it is done with replacement. Okay. This is an important aspect. Now, can you think of one other way in which I can make the decision trees to be different? Can you think of other ways in which you can make the decision trees to be different? Okay, I'll give you one analogy. You have seen this already in decision trees. Can you tell me what this model does? I mean, what this particular hyperparameter does? We just discussed it.
Using different features, different number of features.
So don't you think I can do it for each decision tree?
Yes.
Instead of giving all the features, okay, at every node, can I say that I give a subset of the features at every node?
Yes.
Okay, that is called as max features. This is also called as feature bagging. So you are selecting a subset of the features okay, out of the total features, okay, to create each tree. And this will further ensure that the decision trees are different, right? Yes or no?
Yes.
It will actually cause a lot more diversity if you think about it. Can I say that even if the, let's say, training sets are the same, this will ensure that the decision trees are different?
Yes.
Okay, even if the data set is the same, like the training samples are the same, if you do feature bagging, it will turn out to be diverse. The models will turn out to be diverse. This model is called as a random forest. The name itself tells you why. The name itself tells you why. So you're collecting, you can say that you are training a model with multiple decision trees. Okay. A collection of trees is called as a forest. And because you select your features and samples randomly, please note that samples are selected with replacement. Features are not selected with replacement. It is feature bagging. Okay. It's without replacement. Okay. So basically you select say 5 features at random if you have say 10 features. Okay. So this is without replacement. Okay. And so this random forest, it makes use of a strategy called as bootstrap aggregation. The idea is first you bootstrap your training data into multiple training data sets, and then you aggregate the predictions from multiple models. Okay, then you aggregate the predictions from multiple models. So if you are doing classification, what you will do, how will you aggregate the predictions? Anybody? If you have multiple models, let's say you're doing binary classification. So every model is going to tell you the answer is 0 or 1, right? So what will you finally answer?
Majority.
Majority. So aggregation is done in terms of majority. Let's say you're training regression trees. How will you aggregate the models, aggregate the predictions from multiple models?
Based on the evaluation matrix, whichever. Like
No. I'm saying, let's say D1 predicts the output as 1.3. D2 predicts the output as 3.4. What would you finally predict?
Maybe the mean.
Average, right? One way to do it. Can you do weighted averaging as well? Because decision trees can be having different performances.
Yes.
So you can do weighted averaging also, that we have seen in K nearest neighbors, right? Okay. It's just that performance of the decision tree decides the weightage of it. Okay.
The performance, but like more the weight.
Yes, better the performance, more the weight. Okay. Okay, and aggregation is combining the predictions. All right, so it does two things, bootstrap and aggregation. A random forest does two things, bootstrap and aggregation. Okay, so you can come across these terms. Please note this. Okay, you can come across these terms. All right. So yes.
I can combine random sampling and feature bagging together.
Yes. You can combine them together. Okay. To get even a better random forest. Okay. So what do you think the hyperparameters will be? What do you think the hyperparameters will be?
Number of samples.
One is the number of samples. Okay. What else? The first thing that you see.
Number of features.
Number of features. Okay. And what another? Look at the first row that I have written here. In the first row, what is it that I have written?
Percentage of split.
No. Look at this first row. What is this?
Number of decision trees.
Number of decision trees, which is also called as number of estimators. So P is also called as number of estimators. So for a random forest, there are 3 popular hyperparameters. Okay. So this model called as random forest, it has 3 hyperparameters. Okay. Let me define the hyperparameters one by one. Okay. So one of the hyperparameters is your number of estimators. Basically the number of trees. Next one would be max samples. Okay. How many samples are to be given to each tree? Next one would be max features. Anything else comes to mind? Think about you're creating decision trees. Don't you think I can actually use all the hyperparameters associated with decision trees?
Yes.
So you can use all pre-pruning and post-pruning heuristics. Okay. So there are a lot of hyperparameters for it, if you think about it. Yeah. Because decision trees have so many hyperparameters, right? Okay. This is called as a random forest. You can use it for classification or regression. Yeah. Oh, I made it a markdown. Okay. All right. So shall I just show you how it is implemented directly?
Yes.
Shall I do it on the single train test split? Okay, let's do it on the single train test split. And I'll show you the best results directly. Okay, I'll show you the best results directly. Okay, there is one more thing that I want to show you first. Okay, so let me take a data set. Okay, let me take the same iris data set. Get the features, get the output. Split the data. Okay, so data has been split. Now what I'll do is I'll just train a simple random forest classifier. So it is present in library ensemble. Okay, and you can call random forest classifier. I'm going to show you the default model first of all. Okay. And let's put a random state so you get the same results as mine. So fit it onto your train set. And now I'm going to show you. So basically, you can use the same predict method to predict your outputs. Okay, if you want probabilities, it will give you the probabilities as well. I'm not sure whether it gives predict probabilities. Maybe it normalizes across all the trees. Just give me a second. Okay, so each tree is going to give you what we say is an output as 0 or 1, right? In this case, 0, 1, or 2. Yes or no?
Yes.
So for a given test sample, how many outputs will I have? Equal to the number of models, right?
Yes. Okay.
So let's say I have 100 models. 70 models say that it's a 0. So what percentage of the probability should go to class 0? 0.7. Right? So this is the probability that you will get in terms of the number of models, the percentage of models that vote for a particular class. Okay? Does it make sense? So this is actually the percentage, okay? You can say the fraction of models contributing towards a particular class.
In this case, for the first sample, I can say the output predicted is 2 because that is.
Yes, that is 99 of the 100 models are predicting that it's a class 2. Okay, I believe that the number of estimators by default is 100. Let me just check. I think it's 100. Okay. Otherwise, I'll show you how to set it. Okay. It's called as n estimators. Okay. Can you see it's 100 by default? Does that make sense?
Yes.
Okay. So by default, it is 100. All right. Let's just post it here. Okay. So there is one more thing which random forest gives, okay, which every ensemble learning model will give you, and this is something related to the way decision trees are designed. Okay, I'll ask you this: can I say that decision trees are doing implicit feature selection? Think of how decision trees are built. What is the first feature that is selected at the root node? Can I say that is the most informative feature, one with the highest information gain?
Yes.
And do you remember in when we did this example where the student was, I mean, a person was trying to buy a computer or not?
Yes.
So there one feature was not selected, right?
Yes.
So can I say that decision trees are basically trying to select the important features and implicitly discarding the unimportant features?
Yes.
So they perform implicit feature selection. Now we have multiple decision trees. So do you think that I can look at the root node of all the decision trees and maybe make a claim that, okay, if majority of the let's say if most of the times in the root node of multiple decision trees a particular feature is coming, can I say that is the most important feature?
Yes.
Does that make sense? Okay, maybe some other feature is used at the second level across most of the trees. Can I say that is the second most important feature?
Yes.
Okay, so these ensemble based models, okay, especially this random forest model, can tell you what is the importance of a particular feature in terms of that, at what place they are used in decision trees. So there is this property called as feature importances that you can see to decide which features were used frequently and which were not. Okay, so since we have 4 features, these are the importances of the 4 features. I'll just put everything nicely in a data frame just to show you. So these are the importances of those 4 features. Okay, let's say, okay, index is the feature names. So in my data set, these are the feature names, and I will give a column name. Let's call the column name as importance. Or okay, so look at this. Okay, so these are the importances. Which feature do you think is the best?
Petal length.
Petal length. Okay, you can actually sort this. Let's save it as say IMP. I don't want to go, I mean, writing even bigger codes. Like I can write the code here also, but it will become like quite cumbersome. So I'll just sort the values based on this importance column. Okay. And you can say ascending is false because I want it in descending order.
Spelling of.
Okay, what's the its importance? All right, so you can see petal length is now the best, then petal width, and so on. Okay, so this way you can actually do this. Do you remember we did recursive feature elimination?
Yes.
So you can use this random forest on top of recursive feature elimination. Okay, use RFE with recursive feature. I mean, use RFE with random forests to drop some of the unimportant features. Okay, this can actually help in improving your performance. Okay, can you try it? Just call, replace the model name. We did it with linear regression, right? You replace the model name with now random forest, and rest every procedure remains the same. Okay. Okay. Can you try that out?
Yes.
Okay. Do you want me to do this, or you can try it out? You can do this, right? I hope, because the code is already shared with you. You don't have to do much. Just put the name of the model as random forest, data set to be a classification data set, and try this out if you can improve the results with and without RFE. Okay. So internally, RFE will drop the features based on these feature importances. In linear regression, how does it decide to drop a feature? Based on
Weight.
Based on the thetas, the absolute values of your weights. Okay. So here it will drop it based on feature importances. Okay. So you can try this out. Okay. Yeah, if you are unable to do so, let me know. I'll show you in the next class, or maybe even in this class I can do it, but it's just a repetition of what we have done earlier. Okay. All right. Okay. So this is a simple random forest model. Anything else that you want me to show? Like with simple random forest classifier. So we have seen just a generic model, how to make predictions, how to look at probability scores, how to interpret them. Okay. We have seen model importances. Shall I now do tuning of it?
Yes.
Do tuning of it. Let's see. Okay, what is the accuracy for this first? And let's see if it did better than the test set. It was around 96.67%, right? If you remember, 0.96667. Okay, let's see how much is this time. Is the same. So it's not helping. Let's try to make it better. Okay. By default, when we tuned the decision tree, it came out to be 1, right? Do you remember it? When we tuned a single decision tree, it came out to be 1 on the test set.
Yes.
Let's try to do it for this random forest classifier. Okay. Again, I'll do it in the same way. Okay, I'll do it in the same way. I'll just copy paste the code. That will be easier. I'm going to first try what we say is basically without these pre-pruning and post-pruning heuristics. Okay. I'm going to first try without the pre-pruning and post-pruning heuristics. Okay. Rest everything I'm going to keep. Okay, let's remove this part first. Okay. Or maybe let me keep this part. Okay, it'll just take some time. Okay. I've already imported random forest classifier. So my model is this random forest classifier. Okay, I'll add some more things. Okay, the number of estimators. Let's call it as num. How much estimators do you want? How many estimators do you want? Shall I go from say 50 to say 500? Will that be fine?
Yes.
Okay, shall I go from 50 to 500? Okay. So 50 to 500. I need integers, otherwise it will throw an error. Okay, so I have to ensure this. Okay, I can do it like this. Okay, that with the range, it will be easier. At an interval of 50. Okay, maybe say starting from 100 at an interval of 50. All right. Maybe I'll start from 10, go up to say 200 at an interval of say 20. Okay, that will be, and then I'll go up to 500 if needed. So this is for the number of estimators. Okay, let's convert it to a list so that you can visualize it as well. Okay, what is happening? Otherwise, it will throw a range object. Okay, number of estimators. When max features have already taken, right? Okay, I just need to decide max samples. Let's call it m samples. So m samples would be, let's decide the percentages. I'm going to try from 50% to say 1, maybe say 5 values in between, 6 values in between. Okay. So this is your max samples. All right. Okay, for n in this n estimators, and for p in m samples. I'm calling it as random forest classifier RFC. Okay, let me put these arguments. So number of estimators is this n, and max samples is this p. Okay. All right. In the combination, I'll put n and p also. So after m, I need a comma. And then I need a n. So, and then I need a comma again, and then I need a P. Okay, and then I need a comma here, and this should finish. Okay. All right, looks okay. I hope there is no mistake. Let's see. Is a problem. N estimator is not defined. I defined it. Oh, sorry. What did I call it? Num. All right. There's one more. Okay. Splitter is not there here. Okay, let's see if it does not support splitter. Okay, because see, you're already doing max features, right? So there is no need for splitter. By default, this max value is square root of the original features. So you don't need splitter here. You don't need splitter here because you're already selecting a features, I mean, a subset of features at every node, right? So it doesn't support randomized decision trees. Okay. I'll just remove the split here. Where is the splitter? It's split type. Okay. So what did I do? I, J, K, L, M is removed. Okay. It's one more issue. Where is the splitter?
This random forest
Okay,
plugin.
yeah, here it is. Sorry. Okay. Okay, so it has started computing the accuracy for your different models. Okay. So far it is just giving me the results are the same as 96.67%. Everybody is like at 96.67% only. How many combinations are there total? 3, 4, 5. 4 into 4 into 3, 12. 12 into 2, 24. 24 into 3, 72. 72 into 20. Oh, there are so many. 1440 multiplied by 6. So around 2000 combinations or so. Okay. Let's see if it touches a 1. What was the best combination for our decision tree? It was 4 guinea something, if I remember correctly. What was the best combination? It was 6 to, oh no, this was for regression tree. I want classification tree. What was the best combination? 4 to guinea, right? So let's wait if it touches 4 to. Yeah. So it is still at 3. Okay. Let 4 also come. Probably it will touch a 1 in that case. Any questions? Oh, it's time consuming. Okay, shall I stop it and you guys can run it in your free time? What do you recommend?
Yes.
Okay, I mean, you can run it in your free time, right? I mean, maybe reduce the number of hyperparameters. Or what I'll do is I'll run okay, I cannot run it randomly. I have to select, I mean, I have to make a dictionary and then select some random combinations. Okay, because I'm running for loops right now. So around 4.3, it will give you kind of one, hopefully. So let it come to 4.3 and Guinea, something like that. Or maybe what I'll do is this, I'll just try with these values, okay, these combinations. I'll stop this. I'll stop this. Just give me a sec. Okay, I'll just run for a few combinations only. That way, I'll have the results as well. Okay. I don't need depth. I don't need min sample split. Maybe I'll just take this M depth. Okay, I'll just take one of them. But anyways, I have to still run it again. Okay, you guys run it, okay, in your free time. You will definitely see a 1. Okay. Okay, you guys run it in your free time and definitely see a 1. See, in the same way, you can tune for a random forest regressor model. Okay, this is pre-pruning with random forests. Okay. You can try post-pruning with CCP alpha. Okay, try post-pruning with CCP alpha. All right, so you don't have to change much. Just change one of the arguments as CCP alpha and you can run it with that. I'll show you on I mean, can you do it on a regression dataset also? Nothing would change except for this criterion. Can you do it on your own, or maybe I'll do it for this small dataset that we have? Yeah, I'll choose this. Then I'll do it here itself. Okay. Same concept applied onto another data set. Okay, this would be a random forest regressor. Okay. Rest everything will stay the same. So I have to take max features is already there. I have to take M samples and number of estimators. Splitter I have to remove. To check this. Estimators is N. Okay, looks all right. Let me just check. It looks all right. Okay, so this is your random forest model running. Okay, please note that I haven't changed it. Okay, it's DTR only. Okay, I've given the name as it is. So these are the decision tree regression results. If you remember earlier, the results were around 0.031 for regression models. It was around 0.031. Okay. But this was for CCP. What was the result for single decision tree? It was zero, right? After searching. Yeah, it was zero. Single decision tree did very, very well here. Okay. Okay, let's see what if we can improve upon these. I mean, zero obviously is the best that you can get. See, when you're obviously having multiple models, right? Even if a model is having a slight error, if you take the average across all, it is going to be certainly more than zero. Okay. Hopefully, it will be better than CCP alpha at least. That was around 0.031. Okay. Maybe it is better than this at least. Maybe it is better than this at least. Where is this result? 0.031. Yeah, it will be better than this at least. Okay. Hopefully. Now, can you see any value better than, yeah, this value, can you see it's better than that? Okay, so it is doing better than your CCP alpha for sure. Okay. And you will get even better values like this. This is also better. Okay. Let's see how much closer it can get to zero. It's actually increasing with this poison. Poison is not working well. So you can search for these combinations. I'll stop it here. Okay, I'll stop it here. Otherwise, it will. We have around 1400 combinations that are running. Any other questions? Yes, people. Any other? I just stopped it. Okay, what was the best result that I got at the end? At least around still 0.031 approx. Okay, it's still better than CCP alpha, but not doing better than a single decision tree. Please note that if you do five-fold cross validation, this will actually kind of beat that. Okay. If you do a decision tree, let's say five folds on the same data set, random forest will beat that. Okay, for sure. Maybe I'll just show you that. Okay. So if you run, say, five-fold cross validation, so let's do that. Okay, let's go to model selection. Okay. Import your cross-val score. I'm just running for the best combinations. Okay. Hopefully, for one combination, I'll show you. Okay, it will be beating that. Okay. I'll show you for the default metrics. Hopefully, that is better. Okay. So you are passing your model to be, say, decision tree, say, classifier. I'm passing the default model. Okay. So just to show you, the data is in X and Y cross validation technique. Let's import. Let's take stratified k-fold. Let's do, say, 10 splits. Hopefully, random forest will beat this performance. Okay, and scoring metric is, let's say, accuracy. We are going to take the mean of this. So this will actually give me 10 results. I'm going to take simply the mean of this. Okay. So it is around 0.96. Now let's see it for your random forest classifier. Okay. So you see that it is slightly better than this. Random forest does better than this. See, the split that we have made, right? The train test split. Maybe decision tree does it better on that particular split. But you can see that random forest on average does much better. Okay. On average does much better. All right. Any questions about this? If you do grid search, random forest will definitely outperform a single decision tree. Okay. Any questions as such? Yes, people. You can try grid search, try with different hyperparameters. Overall results over 10 folds will be better. Okay, maybe I'll show that. There's still 5 minutes remaining. I'll do that. Okay. Let's run it with decision tree. You can take some parameters. Okay, I'll try with some parameters only. Okay, my next step is maybe say a range from 2 to 6. Okay. Num sample split. We have 4 features. Okay. It's for binary only this time. Let's run say randomize search CV instead of running grid search. Let's call it hyperparameters. What's the problem? Oh, all right. What was the name of this parameter? Num sample split. Min sample split, my bad. Okay, this is done. So this is your best score. I'll show you maybe one more time. Okay, just running this is not taking much time. 0.96 was the best result so far. Let's see if I run it for a few more times. This is the best that I get with this, around 0.96002. Okay, I don't see a better improvement than this. I've run it 5-6 times, but this is more than sufficient to do this. Okay, so I'll just run this for random forest classifier. Okay. Okay. What's the problem? And you throw an indentation error otherwise. Okay. That's right. Okay, from 0.6, let's say, to 1, say 5 values in between, right? Okay. There's a problem. Split. Hopefully, this value will be better than 96.0002, whatever that value was. Okay, so currently it is around 0.96. If you run it one more time, probably it will beat that value. Okay. But it is certainly going to be better than that a single for that of a single decision tree, for sure. Okay. Maybe try grid search and you'll be able to beat this value. Okay. So you can just try doing grid search here, okay, instead of this randomized search. I'll just write the code for it here itself. Let's see what is the best value that we get. It's still here, the same here. Okay. I'll just change this and you can run it and you will see that it beats those values. You don't have to change much, just change this to parameters grid. Okay, and you will see that, okay, this value would be beaten easily. And do try it out, okay. It will take probably half an hour to do this. I'm not running it, you just try to do this, okay. You'll be able to beat this value. Yeah. You'll be easily able to beat this value for sure. This is S small is here. E is capital here. Okay, any questions? Yes, people. I'll just see, okay, if yeah, it is running. So you can just run it in your free time. Yes, people. Any questions as such? Ask people. Any questions? Tell me, people, any questions? I'm uploading this file to your Drive folder. So you can take a look at it. Maybe if you have time, you can see to it right away. Okay, I've uploaded the notebook and some slides as well that you can refer to. For ensemble learning. All right. So if there are no questions, I'll just stop the session and we'll meet tomorrow to discuss the next topic, which is boosting. It's the better version of ensemble learning. So most of the times it does even better than bagging, which we do it in random forests. Okay, so we'll see boosting tomorrow. Bye everyone, take care.